All right, now let's go into question 2. They say to us we've got a physics learner that pushes a crate, a 34 kilogram crate up the plane with a horizontal force of magnitude F. Right, now they say to us this force is parallel to the horizontal, right? Okay, so as shown in the diagram. Right, so they say to us the coefficient of friction between the crate and the surface is 0.25. Ladies and gents, let's just quickly have a look at this. So if the force is horizontal, then it means that, now remember, whenever we're going on an inclined plane, we are going to actually take, in this case, the force applied. But now the force that is applied is not parallel to the incline, right? So which means what we're going to have to do is take that force and we are going to divide that force into its components, right? So there will be a parallel component of the applied force, right? So let's call that F parallel. And there'll be a perpendicular component of that force that would be F perpendicular. Now, I want you to note, I am not referring to the parallel and the perpendicular component of gravitational force. FG parallel is a different story altogether. So all I'm just simply doing here is that I'm taking, because this force is not parallel to the incline, I would need to divide it into its horizontal or its parallel and its perpendicular components, right? So this parallel component is the one that's actually pushing the force, or rather it's the one that we're going to actually add when we are now doing the calculation, right? And the perpendicular component, and you can see it's actually acting downwards, right? This perpendicular component, and this is the one that is going to actually take the force, or rather affect the value of the frictional force. Right, now they say to us, suggest a reason as to why the coefficient of friction is dimensionless. Now remember that the coefficient of friction is actually a ratio between forces, right? So it's, now if you think about it, we always say the frictional force is equal to the coefficient multiplied by the normal force, right? But both of them are forces, right? So this is force in newtons divided by another normal force, which is in newtons. So newtons over newtons, that makes this dimensionless. So all we need to say is that it is a ratio of forces, okay? Right, or even if you said that the forces rather, or rather the SI units of the forces cancel out, right? So they say to us the crate moves up at a constant velocity. So note, the moment we talk about constant velocity, we know that F net would be equal to 0, right? That acceleration is 0. So therefore it means that the sum of forces that are acting on the trolley or on the crate are actually 0. Right, now they say state in words Newton's first law of motion. Remember, it says that a body will remain at rest or in constant motion in a straight line unless it is acted upon by a non-zero set of forces or an unbalanced set of forces, right? So in this case, let's look at the next one. They say draw a labeled free body diagram for the crate while it is in motion. Right, now ladies and gents, let's quickly do this. So firstly, there is the applied force, okay? We'll come back to that, okay? So as per normal, right, your examiners actually prefer that you do not use the parallel and the perpendicular components, right? So we know that we've got, okay, let me just bring this down a little bit. We know that we've got gravitational force, that's Fg, right? That's going to be the normal force, right? So we know we have the normal force there. We know we've got, in this case, the applied force. But please remember, where is that applied force? It's actually going horizontally. So this is the value of our applied force. Okay, so let's try and draw that nicely there. So this is the force applied. Okay, this is going to be the gravitational force, or let's rather say that is the weight of the object, right? Okay, please, when you label, make sure that you label in full and make sure that your forces are all connected to the dot. Okay, right. Otherwise, okay, let me just draw that arrow a bit nicer. All right. Yeah, I think that's much better. Okay, so there we got our arrow and we've got the normal force, right? There's the arrow. Okay, and right, I'm just dragging this now. Okay, because I'm just trying to get those to be as perfect as possible. Right, so we've got the normal force. All right, and we've got gravitational force, we've got the applied force, but also remember we've got frictional force, right? So friction opposes the motion of the object, and remember that friction is always parallel to the object itself. So we know that the value of our frictional force would be in that direction. So that's friction over there. That's frictional force. Okay, right. Now, you might be asking, was this the only way in which we can draw it? There's nothing wrong if you placed that applied force on the other side, right? So that applied force, as long as we make sure that it is connected, in this case, to it's actually connected to the dot, right? Okay, so let's go to the next portion, right? So we had 4 marks, that's 4 forces. They say using an appropriate calculation, show that the kinetic frictional force acting on the crate is that value, right? Now, remember, if we're going to look for frictional force, okay, so kinetic friction would be coefficient of friction multiplied by the normal force, right? So we know this is going to be 0.25, but I want you guys to please note, how am I going to obtain my normal force? So I'm going to just tweak our diagram a little bit. Please, you draw it like this, but I'm just trying to show you in this case in terms of components. Now you remember for gravity, we've got the perpendicular component. Okay, let me just choose another color that looks a bit clearer, right? So we've got the perpendicular component, okay? And so this is FG perpendicular, right? But we also have the parallel component of the force. So you remember, so instead of having that weight there, let me substitute it with its components, right? Okay, let me just make that nicer. So that is FG parallel, right? And the perpendicular component. Also, remember for the applied force, this was our applied force, but we said for this applied force, there are 2 components, right? And these 2 components in this case are going to be, right? So again, I am drawing the components of the applied force. We said it's going to be F parallel, right? But we also have F perpendicular, which is going down like that, right? But I am going to actually remove the applied force and I'm going to substitute it with its component, right? So this is F perpendicular. Now I want you to note in this case, when we look at the perpendicular forces on this diagram, right, which ones are the perpendicular forces? Right, so it's going to be the normal force as well as Fg, the perpendicular component of gravity, as well as the perpendicular component of the force itself. Right, now before I get to the calculation, we know that when we want Fg perpendicular, this is going to be mg, the cos of the angle of elevation, right? The mass of the crate is 34 times 9.8. This is the cosine of 25 degrees. Now I'm not going to calculate it. I'm going to leave it as is, right? But we also have F perpendicular, the perpendicular component of the applied force. Right, now I want you to please note this. So that means if I look at that angle, that's also going to be 25 degrees. Now, if you think about it, you can use alternating angles to try and prove that, right? So in that case, that force there is also 25 degrees, or rather the angle there is 25 degrees. Now, if you look at the perpendicular component, it is on the opposite side of this angle, right? So this is going to be the sine. So that's going to be F, the sine of 25 degrees, okay? Right, now let's calculate the frictional force. So frictional force would be coefficient multiplied by the normal force. So that will be 0.25 into, now note both forces are actually working against the normal force. So the normal force would be the sum of those two perpendicular forces. So this would be Fg perpendicular plus the perpendicular component of the applied force. Right, so 0.25 into, so we said that value there, 34 times 9.8 cos 25 plus F sine of 25. Okay, now let's get to the part where we are multiplying, right? So I'm multiplying the 0.25 to this value. 0.25 times 34 times 9.8, the cosine of 25 degrees. And I get 75.4, well, 75.5, right? 75.5. And then I've got plus 0.25 times sine 25f. So I have 0.105 f. Right, now ladies and gents, let's see, does this look okay? They said 106. Actually, that's correct, 106, because we are right. So if you look at this, they left it to 3 decimals. They said 75.495. Okay, so I'm going to leave it as they did, 75.495 plus 0.106 f. So this is the expression for the frictional force. I hope you got that. Right, and then they say to us, hence or otherwise, calculate the magnitude of the magnitude of force F. Now that we know that force, or rather the frictional force, is that value there, right? What other force is acting here? Remember, now we are looking at the forces that are actually acting parallel to the incline. And we know the sum of those forces is actually equal to 0, right? So we're going to say the parallel component, so the sum of forces, right, that are parallel must be equal to 0, right? So now what forces do we have? We've got F parallel, okay? We've got minus frictional force, that is minus FG parallel, and this is equal to 0. Now, ladies and gents, all that there simply is to it, we just need to find our F parallel value. Now remember, this is cosine, so this will be F, the cos of 25 degrees, right, minus this entire thing that we just found, okay? So that is going to be minus 75.495 minus 0.106 F. Now remember, multiplying it by that negative that's in front of it, okay? And this is minus FG parallel. This is going to be the mass. So this is 34 times 9.8. Okay, if you don't mind, ladies and gents, I'm just going to erase this so that I'm able to answer that question. So this would be equal to, right, 34 times 9.8, the sine of 25 degrees. And remember, we said the sum of forces is equal to 0. Now let's take all the like terms. I've got these two in terms of F, right? So what is F cos 25? Okay, so that's 0.906. Okay, so remember they took to 3 decimal places, 0.906. Okay, right? F minus 0.106 F, right? And I'm going to take all the values, so these ones I take to the other side. Remember, this becomes positive and that becomes positive as well. So I'm going to take 75.495 plus 34 times 9.8, the sine of 25 degrees. And this would give us 216.311. Okay, now if I subtract those two from each other, I get 0.906 minus 0.106 gives me 0.8, right? So 0.906 minus 0.106, that gives me 0.8 F. Okay, and this is equal to 216.311. And if I divide both sides by 0.8, what I get there is the value of F. So 216 rather, apologies there. So 216.311 divided by 0.8, and I get that force to be 270.39 newtons. All right, so I hope that makes sense, ladies and gents. Hopefully you were able to follow on that parallel and perpendicular components of the force. Right, so we are done with that. Now they say to us for 2.2, the mass of the earth is 5.98 times 10 to the power 24 kilograms, and the radius there we are given. They say mass of a satellite is 1,000 kilometers above the surface of the earth, and the acceleration towards, or rather is accelerating towards the earth. So we've got a satellite that is accelerating towards the earth. They say the only force acting on the satellite is the gravitational force of the Earth. Right, they say if the weight of the satellite is 3,660 newtons, right, at 1,000 kilometers above the surface of the Earth, calculate its weight on the surface of the Earth. Now, I want you to really think about it, ladies and gents. So there it is, we've got a satellite, okay? Actually, that's the Earth. Let's say we've got the Earth there, and we've got a satellite. And they said this satellite is 1,000 kilometers away from the surface of the Earth. This is 1,000 kilometers. And what's happening to this satellite? Okay, let's say here's satellite S. That's the Earth, E, right? So the Earth is actually pulling the satellite towards itself. Now let me indicate those forces, right, that are acting there. So they say to us, the satellite is being pulled towards the Earth, right? So we want to know in this case, we've got the mass of the satellite. Where is this? Yeah, so actually they said if the weight of the satellite is 3,600 newtons, 660 newtons at 1,000 kilometers, right? So which means the force of attraction, right, so is going to be G. That's the mass of the Earth, the mass of the satellite, divided by the radius, or rather the distance. But I want you to think about it. What's our distance? It's going to be the center of the Earth, right, plus this 1,000 kilometers, right? So we're going to say the radius of the Earth plus the distance d, which is squared. So let's substitute there. We know the force of attraction is 3,660 G. Okay. All right. So we are saying the mass of the Earth, we've got it over there. That's 5.98. Okay, the value of G, I don't think that's the correct one. Let's go and check in our data sheet there. Right, so G, where's our table of constants? Right, so there, 6.67. Why did I forget that value? Right, so that's 6.67 times 10 minus 11 multiplied by the mass of the satellite. Now remember, they had not given that to us, right? So this is divided by, okay, so we are going to have, right, so we're looking for the mass of the satellite, right? So that we can determine its weight on the surface of the Earth. So we're going to say, right, divided by the distance from the Earth, 6.38 from the center of the Earth, times 10 to the power 6, plus the 1,000 kilometers. Now remember, when we say 1,000 kilometers, that's going to be 1,000, right, times, remember kilo means times 10 to the power 3, so that's going to be actually 1,000 times 10 to the power 3, which is actually to the power 6. Okay, but remember to square that. Now let's look for the mass of this guy. Please make sure the mass of the satellite. Okay, so I'm going to cross multiply there and divide by what's in the numerator. So 3660 multiplied by, okay, that's 6.38 exponent 6 plus 1 exponent 6. This is squared Okay, and I am going to divide all of this up by 6.67 exponent minus 11 times 5.98 exponent 24. Right, and ladies and gents, let's see. No, I said plus instead of multiplied by. Apologies there. So this is supposed to be multiplied by. And I get the mass of this object, of this satellite, to be 499.7. Okay, if you want us to be precise, I'm going to say 499.77. Okay, I would have said 500 kilograms. Right, 499.77 kilograms. Now remember, we're looking for its weight on the surface of the Earth. All we need to do is say W is equal to mass times gravitational acceleration, right? So W is equals to M times G. This is 499.77 multiplied by 9.8. And if we get that, ladies and gents, actually, let's see, can I get that answer back? Nope. Okay, 499.77 multiplied by 9.8, and I get the weight on the Earth would be 4,897.75 newtons. Remember that weight is actually a force, and forces are quantified in newtons. Ladies and gents, that is how the cookie crumbles. I hope that you got it in terms of question 2. Really, really interesting. Okay, let's go to the next question.